Hello guys and welcome. In this video we are going to talk about electrostatic forces and electric fields. This will be in continuation to the block which you must have read already. What are actually electrostatic forces? Before talking about forces, let us first talk about charges. So whenever we talk about charges, there are primarily two kinds of charges. One is definitely positive and the other one is negative. The unit of any charge, in fact, the SI unit of the charge is represented by C, which is Coulomb. Usually the charges you might see in the questions are because 1 Coulomb in absolute terms is actually a very large or very big charge. It's a very big value. So in the questions, you will primarily see the values to be in microcoulombs and so because to be in the practical physics, this is a pretty big value. So we don't deal with such higher values of charges. Positive and negative charges are these two are the two charges in which we have been dealing, and all the electrostatic forces and everything more or less depends on these. Just like we have a force due to the gravity, which the equation denotes as mg, where g is the gravity constant, which is 9.8 meter per second square, and m is the mass. So in all this, just like the force of the gravity, we have a force due to electrostatic charges, which we usually represent by Fe, and definitely there is an arrow above it which represents that the force is actually a vector quantity. So this equation of force is given by is known as the Coulomb's law, which says that the force in between any two charges Q1 and Q2 is given by K times Q1 Q2 over d square, where we represent that these are the two charges which are Q1 and Q2, and they are separated by a distance of d. If we want to get this, and K is definitely the constant of proportionality. So from here, we can see that the force is directly proportional to the product of the two charges, and force is also inversely proportional to the square of the distance between the two charges. It means that if we keep on increasing the magnitude of these two charges, the force will keep on increasing, while if we will keep on increasing the distance between the two charges, then this force will this force will keep on decreasing because it is inversely proportional to the square of the distance. So when we combine these two proportionalities, we definitely have to put a proportionality constant, which we represent in this case by K. Now, if we talk about the unit of force, definitely the SI unit would be newtons. If we need this force in newtons, then the charges Q1 and Q2 must be in coulombs, and the distance d must be in meters. So everything should be in SI unit for the force to finally come as newtons. Let's talk about this constant K. This constant K, proportionality constant K, also has a value which is 1 over 4 pi epsilon naught. Now, what is epsilon naught? Epsilon naught is called as permittivity of vacuum. So this I have already talked about it in the blog. So this is called permittivity of vacuum. And what is the value of K? This is 9 times 10 raised to the power 9, and the unit would be nm square per coulomb square. So this is the usual value of K, but mind it, this value is applicable when the medium is air. But if we say that the two charges are placed in any other medium, then its permittivity, or this value of the constant K, the net value of the constant K would change. But in most of the cases, the medium around the charges would be the air. So this is how the equation of the force looks like. And let us look at a couple of examples. So we have two charges which are placed at a distance of 1 meters. The unit of both the charges are 1 coulomb, and this is, or let's say 1 microcoulomb, and this is -1 microcoulomb. This is point A, this is point B. So we have to find the force on the charge B due to the charge A. So we know that the formula for the force would be K times Q1 Q2 over D square. So let's substitute the values. We'll not put the value of K because that's ultimately a constant. We know its value. We're just interested in the other values. So we have 1 as the Q1, but this is microcoulomb, so we're going to convert it in coulombs. So we're going to raise it to 10 raised to 6, 10 raised to -6, pardon. Likewise, we have the other charge, which is also 1, but it's of opposite sign. So we have -1 times 10 raised to the power -6 over we have the distance separated by 1 meter. So we have 1 square. So if you are going to simplify this, we have k times 10 raised to the power -12, and the value of k is 9 times 10 raised to the power 9, and this will be 10 raised to the power -12. In order to solve these two exponents, since the base is same, the power is gonna add, but since there is a negative sign over there, so ultimately it's going to subtract. So it's 9 minus 12, and 9 minus 12 is nothing but 10 raised to the power -3, and the unit would be newtons, or we can say that the force is 10 micro newtons. So this is the force, and if you will notice, we have here not placed any minus sign, which is due to this charge. That is because minus sign just represents the direction. So either we can say that the magnitude of the force is 9 micronewtons, while the direction will definitely be an attractive kind, because the charges of, unlike uh, the two opposite charges, positive and negative, have an attractive force. So the force would be force due to the charge A on charge B would be in this direction, while the force on charge A due to charge B will definitely be in this direction. So they have an attractive force, while the two charges of the same sign, whether they are positive and both are negative, they have a force of repulsive in nature in between them. So let's talk about another example with a little more complicacy. So we are going to now place the three charges at the vertices of an equilateral triangle. So this is how the equilateral triangle is. Uh, Again, the charges are 1 microcoulomb, and let's say this is -1 microcoulomb. For simplicity, we are going to assume that each of the side is of 1 meter. Since this is an equilateral triangle, so all the sides would be of equal length. Let's mark the vertices as A, B, and C. Now we're going to find the net force on the charge C. So definitely the net force would be the combination of the forces due to A and due to B. Let's talk about the force. Let's talk about the force on charge C due to the charge A. So force on charge C due to charge A will be K times magnitude of the charge 1, which is 1 microcoulomb. So 1 times 10 raised to the power -6. Again, -1 times 10 raised to the power -6 over d square. So that will be 1 square. So this is exactly like what we solved in the previous equations. We're going to get the same value as 9 millinewtons, or let's say 9 times 10 raised to the power -3 newtons. And definitely the force on charge C due to charge B will also be the same, because everything is same. The two charges are same, the distance is same. So we can say that the magnitude will again be 9 times 10 raised to the power -3 newtons. But here's the catch, because we need to find the net force, but we cannot really add both the forces right away. So we cannot say that F net will be FCA plus FCB. If you are going to write this, this is actually an incorrect representation. But if you are going to place a vector sign on both, then yes, this is right, because we always have to remember the force is a vector quantity and it's not a scalar quantity. So if we are going to add the two forces, we have to pay attention on what is the direction in between the two forces. So if the force is like this, one of the forces like this, other force is like this. Uh, so this is 9 times 10 raised to the power negative 3. This is 9 times 10 raised to the power negative 3. But mind it, there is an angle between the two forces. And yes, why the direction is in why the arrows are pointing towards this direction is because we have the force is between the positive and a negative charge. So that's going to be attractive in nature. So this is the force due to the charge A, and this is the force due to the charge B. So these two forces now have an angle in between them, and we now have to recall the properties of the geometry of the equilateral triangle, that all the angles of an equilateral triangle are of 60 degrees. So we are going to write this as 60 degrees. So basically we have to do a vector addition of these two forces having an angle of 60 degrees. And we know that by the formula of the vector addition, the net magnitude can be written as f1 square. Rather, I will write it like this. So it's fca square plus fcb square plus 2 times fca fcb cosine of theta, where theta is the angle between the two forces. So let's place the magnitudes. So this is 9 times 10 raised to the power negative 3 whole square, plus this is 9 times 10 raised to the power negative 3 whole square, plus 2 times 9 times 10 raised to the power negative 3, 9 times 10 raised to the power negative 3, and here we have cosine of 60 degrees. Let's try to simplify this. So all these values, as of now, we are not expanding it, because it's better not to expand and find the actual values right now, because there are various things which are going to come out common, and it will simplify our calculation. So cos 60 is 1 over 2. So we are going to write 1 over 2 over here. Unfortunately, this 2 and this 2 gets cancelled. Now, if you notice that there are 3 terms of this kind, because all 3 are same. So we can write this as 3 times 9 into 10 raised to the power negative 3 whole square, which can further be simplified as square root 3 times square root of an squared term. So the square root and square will just cancel out. So we are left with 9 times 10 raised to the power negative 3. So the final answer comes out as 9 root 3 times 10 raised to the power negative 3 Newton. So this is the net force on the charge which is placed on one of the vertex due to the other two charges. So in the case when we notice that the difference between this example and the previous example was, since there were only two charges, we don't have to bother about any other force. We don't have to bother about any direction, but let's say a combination of two forces. But in this case, whenever the charges are 3 or more than 3, and we are supposed to find the net force or any of the charge, then definitely we have to bring in all the concepts of vectors, angles, vector addition, etc., because the addition of vectors is not as simple as the addition of scalars. Let's talk about another example to get the concept clear. So in this case, we are going to assume that all the charges are placed in at the vertices of a square. So this is a square. Let's say we are going to mark the vertices as A, B, C, and D. This is 1 microcoulomb. This is also 1 microcoulomb. This is also 1 microcoulomb, while this is, let's say this is also 1 microcoulomb. So we have to find the net force, and of course, since this is a square, then all the sides are same. So we are going to assume that all the sides are of 1 meter each. We are going to find the net force on charge D due to all the three charges. So the magnitude is again going to remain same. So if we talk about the force on charge D due to the charge A, So the force would be equal to K times Q1, Q2, which is again 1 microcoulomb and 1 microcoulomb. So 1 times 10 raised to the power negative 6 times 1 times 10, negative 1 times 10 raised to the power negative 6 over 1 square. So this is again 9 times 10 raised to the power negative 3 Newton, just like the previous two examples. Likewise, the force due to C on D is also going to remain the same because everything is same except the direction, which we are going to talk uh, after a couple of minutes. And the last charge which is remaining for us to account in our calculation is the charge B. Uh, so there's one extra effort which we are gonna do in this case is the distance between B and D, because the distance is no longer 1, it is along the diagonal. So know that if this is 1, this is 1, then because due to the Pythagoras theorem, this side is gonna be, or the diagonal is gonna be square root of 1 square plus 1 square, which is nothing but square root 2. So let's plug in all these values and find the force on D due to the charge B. That will be K times, the charges remain same, so it's 10 raised to the power negative 6, negative 1, 10 raised to the power negative 6 over, the only difference is this is going to be root 2 square. So K is 9 times 10 raised to the power 9, this is 10 raised to the power negative 12 over 2. So the only difference is this force is going to come exactly half. So it is 9 over 2 times 10 raised to the power negative 3 newtons. This is the force on D due to B. Right. So now we have all the magnitudes. Now what matters is we have to show the direction so that it helps us to find the net magnitude. The net magnitude. Here we won't really have the negative sign because the charges which we assumed are all positive. So let me make that correction here. This also won't come out as negative, and yeah, that's it. So let's talk about the direction now. So the direction in this case would be due to A on D, it will be repulsive, so it's over here. Due to C on D, it's repulsive, so it's over here. And due to B on D is also repulsive, but mind it will be along the side of the diagonal, so it's gonna be in this direction. So now we are gonna add all these three forces which are all in different directions. So let's talk about the first two forces, but here also one thing which we have to notice that since this is a square, then this angle is going to be 45 degrees because this is 90 and these two sides are equal, so these two angles are going to be 45 each. So we can say that the angle between these two forces due to A and C is 90 degrees. So we are gonna find the net magnitude first off due to C and D. So due to C and D, the forces look like this, and there's an angle of 90 degree in between them. So the net force is a simple vector formula. If the magnitude of both the forces are going to be same, let's say it's F and F, which we know it is same because both are 9 times 10 raised to the power negative 3. So if both the magnitudes are same and the angle between them is 90 degrees, so the net force will be root 2 times the magnitude of any one force. So it's gonna be 9 root 2 times 10 raised to the power negative 3 Newton. But we also have to know the direction. So the direction will exactly be at the center. So it's gonna be in this direction, which is, since it is at center, so it's gonna be 45 from here or 45 from here. So that's how F net is gonna look like. And this is just due to the C and D. And now we talk about B. So fortunately, B is also in the same direction. We know that B is along the diagonal. So this is how FB is gonna look like. And this is also 45 degrees. So the net force, since both the forces are in the same direction now, So the net force would be simply the sum of these two forces, because whenever the vectors are in the same direction, we can simply add them. So F, the final force due to all the three forces would be F net plus force due to B. So that's going to be 9 root 2 times 10 raised to the power negative 3 plus 9 over 2 times 10 raised to the power negative 3. And definitely the direction will also be along the diagonal. So it's going to be like this. We can say that the direction is 45 degrees below the horizontal axis, or let's say anti-clockwise towards the horizontal axis, and this is how it's diagonal. So it's just along the side of the diagonal, we can say. So this would be the final answer. So we see that in electrostatic forces, it's very important to know the direction of all the forces, because whenever there is a direction, it involves vectors, and whenever we have vectors, we have to take care about the addition or subtraction, whatever is the case. So that is all about the electrostatic forces. Just to give a brief idea, let's talk about the electric fields now. Electric field is just an extension to the electric forces. The only difference is if we talk about two point charges A and B, which has Q1 and Q2 at A and B respectively, then if they are separated by a distance d, then we say that the force due to A on B would be K times Q1 Q2 over D square. We already talked about this. But what about we want to find the electric field at B? So what we do is we just replace Q2 by a test charge, which is 1 Coulomb. So if we replace that by a test charge, then the net electric, the field, electric field would definitely be KQ1 over D square, which is actually nothing but F over Q2. So electric field due to a point charge is given by this formula, and the direction for the electric field depends on what the sign of Q1 is. So if we talk about the point charge Q, and if this point charge is positive sign, then the electric fields would be going out from this point charge. So it will be like this, radially outwards. While if we talk about a negative charge, then the electric field would be coming towards it. So it will be like this. So this is the property of electric fields, that whenever we have a positive charge, it goes away from it, while if we have a negative charge, it comes towards it. And if we have the two charges in proximity, let's say this is positive charge Q and negative charge minus Q, and if we want to draw the electric fields, then definitely it emerges from positive Q and it goes to negative Q. So that's how the field lines would look like. That it always start from positive Q, and if there is a negative Q, it will terminate on it. If there is no negative Q, then it will terminate at infinity. So this is how the charges will look like, and some of the lines will go till infinity like this, and some of the charges will come from infinity like this. So that's how we represent the electric field lines. And another important point which we have to remember about electric fields is they don't intersect each other. So this is again a property of electric field lines. So this is just an electric field due to a point charge. What if we have another kind of charge? Let's say we have a line charge, infinite line charge, in fact. So if we have a line charge of infinite length, which is, let's say, represented by this, and it has a charge which is distributed as lambda coulomb per meter, as in every 1 meter has a charge of lambda coulomb. And if we have to find the electric field at a perpendicular distance r from it, then the electric field at this point is given by lambda over 2 pi epsilon naught r. This is the formula for the electric field, which definitely comes handy in various questions. If we talk about the electric field due to a circle and rather at the center of the circle, so if this is a circle and this circle has, let's say, a positive charge, it doesn't matter what kind of charge it is, whether it's positive or negative, the value is going to be same. It has a positive charge Q distributed uniformly across the circle, and we're going to find the electric field exactly at the center O. Then electric field at the center O is going to be 0. And why is that? Because due to the symmetry, if let's say there is a small charge dq over here, and there will definitely be an equal magnitude charge which is exactly diagonally opposite to it. So whether it creates a magnetic field, it creates an electric field which is in this direction, then this is going to be cancelled out with the electric field which is going to created by this this point, this small charge. So it will be in this direction. So these two forces are going to cancel out, and then this way all the electric fields, whether you take anywhere on the circle, it's going to be cancelled out with an exact same charge which is diagonally opposite to it, since there is a circle. Due to the symmetry, its electric field is going to be 0. And let's talk about another formula which is very often used in the questions, which is about a ring. So if this is a ring and it has again a uniform charge distribution of Q across it, and we're going to find the electric field at a distance, let's say r, from the center, and its charge is Q and its radius is r. Then the electric field due to this, I'm going to walk you through the derivation of this, how to find the electric field at any point on the axis of any ring. This derivation should be actually learned as a concept, because it not only helps you to find the uh, an electric field on a ring, but on various other such figures. So what I'm going to do is, at the center, at the distance of r, I'm going to take a small charge dq, and I'm going to find the electric field on this point. If the center is O and this point is A, then I'm going to find the electric field at A due to this point charge. I know that this length is this is a right angle triangle, so this length is going to be square root of r square plus r square due to the because of the Pythagoras theorem. So if I'm going to find the electric field, which is represented by dE due to the charge dq, that will be dq, because the dq will now be considered as a point charge. It will be dq over, it will be dq, it will be rather k dq over r square. So r square is going to be the square root of r square plus r square. So square root will go off, so we are just left with this value. But we also have to talk about the direction. So if we are going to assume that the charge is positive, then the direction would be definitely be towards this. Let's talk about this angle, what angle is going to form here. So let's say this angle is theta, then definitely this angle will also be theta, since it is vertically opposite angles. So what about, let's talk about the components of these two. So we are going to make two components. One is towards horizontal and one is vertical. So the horizontal component is going to be dE cosine theta, which is towards here, and the vertical component is going to be dEy, which is dE sine theta. Right, so let's talk about another point charge another small point charge dq, which is diametrically opposite to it. Definitely, this will also create an electric field at the same point, but its direction will be somewhat different, of the same magnitude but of different directions. So it is over here. So if you're going to make an, since this is due to symmetry, this angle is also going to be theta. So this is also theta. So if the green electric field, we are going to make components. So although the horizontal component is going to be same, which is dE cosine of theta and in the same direction, but mind it, its vertical component will be of the same magnitude but exactly opposite direction. So what it means is these two guys are going to cancel out each other because they are in opposite directions. So just like this, all the point charges which we take on the string, its vertical component is going to get cancelled and the horizontal component is going to be added. So what we can do is we are going, in other words, the net electric field is going to be in the x direction, and its value is determined by k dq over r square plus r square times cosine of theta. The only thing which we have to do is we have to determine what this cosine of theta is. So this cosine of theta is going to be the base over hypotenuse. So the base is r, hypotenuse is this. So let's replace the cosine of theta by r over, this remains as it is, and r over r square plus r square raised to the power 1 over 2, and we have to integrate this. So if we are going to simplify this, this will be kr over r square plus r square raised to the power 3 over 2. And since the only variable is dq, we are going to integrate dq. And dq, when integrated over the complete ring, is going to give us q. So the net electric field comes out as kq r over r square plus r square raised to the power 3 over 2. And this is definitely in horizontal direction. So this is how this is a derivation which will definitely help you in finding the net electric field due to other figures, because it's really important to go through this derivation. Although in the end we just have to remember this value to solve the questions, but this concept helps us to actually understand that how an electric field is going to be calculated in some odd figures, which you might see in your examination and assignments. So that's it for this video, and if you have any particular questions, please drop it in the comment section and we'd be happy to assist you further on that.